Hello, makers. One of the more quintessential, or shall I say ubiquitous DIY projects any aspiring maker can take on is that of the outdoor weather station. These pillars of meteorological prognostication are a most wonderful way to learn about not only atmospheric science, but also electronics, mechanical engineering, and computer programming. In many ways, they're a perfect project as a foundation for STEM learning. Some of you may have heard the term the Internet of Things. Simply put, it means adding wireless connectivity to devices or objects that historically have been standalone. In the home, you might have a smart appliance, like a refrigerator or washing machine that alerts you when you're out of milk or your laundry is finished, or even a light bulb you can turn on and off with a phone app would be considered an IoT device. Businesses use IoT in a variety of ways, from tracking shipments of perishable items to monitoring inventory. Agriculture also uses IoT infrastructure to monitor field conditions or livestock processes to make food production more efficient. The introduction of low-cost Wi-Fi enabled electronics in recent years has enabled makers to incorporate wireless connectivity into their own projects. While there are many examples of consumer weather monitoring products available online, the goal of this challenge will be to construct the core elements in a DIY fashion and only purchase components that cannot be fabricated easily or inexpensively. Where possible, we'll try to upcycle components or recycle them to further reduce costs and highlight the utility of saving what otherwise might be thrown away. A weather station can be a rather complex system when viewed from the perspective of its constituent parts. There are the individual sensors themselves, each with their own theory of operation, some type of computer system to capture and store data, along with a wireless system for data transmission. There is also a computer system at the receiving end that logs and displays the data. There's a power supply, a battery, and charging electronics as well. And of course, the mechanical elements, such as the enclosure and supports that protect the whole system from rain, wind, and the hot summer sun. First and foremost, we need to decide what atmospheric data we want to collect. Temperature, humidity, and barometric pressure are easy since all three parameters can be captured by a single device that is inexpensive, small, and consumes low power. An integrated circuit, such as the BME280, combines all three sensors and has a software library for the Arduino platform, so programming with it should be straightforward. Ambient light will give us information about sky conditions and should be easy to implement with one sensor. Wind direction and speed, as well as rainfall, are going to require more care and design, as not only is there an electrical aspect, but a critical mechanical one as well. There are many more parameters that we could capture to create an ever more complex image of our environment. CO2 concentration, particulates such as dust, smoke, and pollen, noise pollution, background radiation, the list goes on. Feature creep is a term used in software development that describes the ever-growing list of desired features relative to the resources and time available to design, test, and implement said project. A maker's project is no different. Each additional feature we want a design to incorporate will take time not only in the design phase, but also fabrication, coding, testing, and final integration. The core parameters we're going to capture are temperature, humidity, barometric pressure, ambient light, wind direction and speed, and rainfall. Now that we know what we're going to measure, we need to focus on the how. When I started the research for this project, I spent a lot of time trying to understand what the state of the art was. What commercial options were available? What could I buy? How were our other weather stations built? What DIY projects are already out there to draw inspiration from? And there is a lot of information available. For about $150, I could buy a personal weather station that includes all of the features I want, and this sets a price floor for the project not to exceed. For about $80, I could have purchased both wind speed and direction indicators along with a rain gauge. I passed on this as the root goal of this challenge is to build these components. Heading over to Instructables.com and Hackaday.com to look around produced a wide selection of DIY weather station projects of varying complexity and provided a good foundation of examples to reference. Finally, I found this excellent technical resource produced by the World Meteorological Organization titled The Guide to Meteorological Instruments and Method of Observation. This exhaustive guide has been in publication since 1954 and is an excellent resource on weather station design, and if you're interested in a rigorous and scientific approach to meteorological observations, I would suggest taking a look at it. For every DIY weather station project out there, there are as many solutions to record, store, and display the data collected. What I need is an existing project that I can leverage to handle all the data collection and storage, but also include a visualization system to make graphs and charts. Something free and open source, something with room to expand, a nice collection of plugins with good community support too. Hey, it's Home Assistant. Home Assistant is a smart home automation system that works with over 1,000 different devices and services, such as Amazon Alexa, Google Assistant, smart lights, thermostats, fans, dehumidifiers, or media players such as smart TVs or connected speakers. HA is truly a hub for the smart home and is perfectly suited to receive data from our weather station, and with the added benefit of being able to use that data later on if I want to. I had mentioned feature creep earlier as a cautionary tale not to pile on every feature right away. Using Home Assistant as the user interface gives us tremendous amount of flexibility going forward to add new features and devices later on after the foundation's laid. The final plus for using HA is the ESPHome plugin that makes programming and maintaining wireless devices based on the ESP8266 chip a breeze. HA typically runs on a Raspberry Pi, so if you have one on hand, you already have the hardware necessary. I'm not planning on putting the weather station on the internet, so both HA and the weather station will live on my home network or the lab network here in the makerspace. At the time of this recording, Raspberry Pis are in extremely short supply and have been so for much, if not all, of 2021 and 2022. It is possible to install Home Assistant on a standard PC hardware running Linux, and instructions are available on HA's website. If you'd like to know more about setting up and running a home automation system like HA, check out the Home Automation subreddit on reddit.com. There you'll find a great community with a wealth of knowledge and practical experience. It's easy to take for granted the circuits whose purpose are power. We plug a device in to charge it or install a battery, and that's the end of it. Our weather station will require power 24/7 and will not have access to mains electricity. As such, we need to decide on a method of power management sufficient to meet the demands of the complete system. While a large enough battery could most likely power the system for up to 30 days or more if care is taken to optimize the finished system for energy efficiency, the battery would be large, expensive, and add the inconvenience of having to be swapped regularly. A wind turbine would be impractical for a number of reasons. Their size and additional requirements for support combined with added costs point to one correct solution: solar. With solar, we can generate usable power over most sky conditions and store it in batteries to sustain nighttime operation. The question becomes, how much power will a solar panel need to produce to cover the total power requirements? Before we can answer that question, we'll need to know more about the power consumption of each component and take that into consideration when making a selection. At this point, we know we'll need a solar panel, a battery, and the circuitry to manage the two. A microcontroller is essentially a very small computer that lives on a single integrated circuit. They're not as powerful as a Raspberry Pi by comparison, and they're designed for embedded applications for a specific purpose. There are several flavors of Esp Development Boards available depending on the project needs, and typically I start with the Node MCU. The Node MCU board has all the creature comforts associated with a development board: USB programming, onboard voltage regulator, and can plug easily into breadboards for prototyping. When powered on, the Node MCU will draw between 70 and 80 milliamps of current when doing absolutely nothing, and about 120 milliamps when using Wi-Fi. We can make some assumptions about operation to get an idea of how much power on average the system might consume. Typical update intervals for weather stations phoning data home can be up to a minute or more, so most of the time the microcontroller is doing nothing. We'll also assume that the power draw from the sensor suite is an order of magnitude less than the microcontroller. To make the math simple, let's say that the entire system draws 100 milliamps, or zero point 0.1 amps. The battery capacity formula is advertised capacity in milliamp hours divided by the load current, also in milliamp hours. So a 1000 milliamp hour capacity battery would be able to supply 10 hours of power at 100 milliamp current of draw. In North America, the shortest day of the year clocks in at about 8 hours and 30 minutes of daylight sometime in December. So our battery would have to deliver about 16 hours of power at the extreme. I'll be using two 18650 cells as the battery bank with a total capacity somewhere between 2 and 3000 milliamp hours range, which should give us a 24-hour reserve window. The solar panel I have for this project comes from a spare parts bin and has no identifying markings, so we'll need to do a little detective work to determine if it will be a good fit. In bright sunlight, the panel produces just under 23 volts, and the cells are encased in a weatherproof material, which is good. So all we need to do is secure it to the main mast. Since the battery charging circuit is sized appropriately and treated as a separate subsystem, if the panel can't produce enough power during the day, we can always replace it with one that does later on. Finally, let's take a look at the hardware we'll use to enclose the electronics, as well as the materials we'll use to construct the mast and support structure. The electronics will live inside of this weather-resistant enclosure that also came from a spare parts box. Enclosures like this are common in the telecom industry, and you may have several outside of your home or apartment that bring in services such as TV, phone, or internet. This one's missing the gasket that seals the two halves together. I'll see about printing a replacement for it in the next video when we cover assembly. I've also used our 3D scanner to make a digital representation of the case so I can experiment with placing the batteries and electronics inside to make the best use of the available space. If space becomes an issue, we may have to use a different enclosure altogether. The main mast and support arms will be made from recycled metal tubes. I think these came from an old clothing rack, and I have several different diameters available. Metal tends to be one of those materials I'll keep around if something's being thrown away, as tube and bar stock are easy to store and are useful later on. We'll be 3D printing brackets and other components as needed, and I expect many of the sensors will have a 3D printed component as well. The outdoors is a harsh environment for common 3D printed filaments, and to get the best possible resistance to UV and heat associated with strong sunlight, I'll be printing with white ASA as opposed to PLA or ABS. To measure wind direction, we need to translate the position of the wind vane into a signal that accurately represents its position. In some examples, a series of magnetic reed switches were used which gave a rough approximation of wind direction, so north, northeast, east, and so on as the magnet passed each sensor. Another method for reading the absolute angle would be to use a magnetic rotational sensor such as an AS5600. This sensor works by detecting the rotation of a magnetic field perpendicular to the sensor, so a rotating magnet directly above the sensor will record absolute rotation with degree resolution. For wind speed, a simple magnetic reed switch can sense each full rotation of the sensor, and with proper calibration we could deduce the wind speed. The drawback with this design is a limited sensitivity for wind gusts or calm conditions, as a complete rotation would be necessary to trigger the sensor. Again, since this sensor rotates, wouldn't it be nice to use the same sensor as the direction indicator and reap the added accuracy? And we can. Rainfall gauges can be as simple as a funnel feeding a graduated cylinder that is visually read by a person. Electronically, they're a little more complex, which is something I discovered when browsing through Section 6 of the Guide to Meteorological Instruments. Precipitation is defined as, quote, the liquid or solid products of the condensation of water vapor falling from clouds or deposited from air onto the ground. It includes rain, hail, snow, dew, rime, frost, and fog precipitation. Unquote. We have the flexibility to add a more complex sensor later on, but for now we're going to stick with measuring accumulated rain and the rate at which it falls. To do so, we'll make use of a tipping bucket gauge, which is a relatively simple device. A receiving bucket set on a pivot will fill with water and tip to one side as it drains, when a known quantity of water fills the bucket. A sensor detects each tip of the bucket and increments a tally of tips. Using the total number of tips and the volume of each tip over a given time frame produces a precipitation rate and total accumulation. As I had mentioned at the beginning, temperature, humidity, and barometric pressure will be the easiest to implement as all three sensors are incorporated in a single package. The only thing we need to be mindful of is enclosing the sensor in a housing that will protect it from direct sunlight, as temperature measurements are very sensitive to their surroundings, so a proper radiation shield will be necessary. We'll 3D print the structure using the UV-resistant ASA filament to give it the best possible durability outdoors. So far we've covered the initial plan and selected our core set of components. In the following videos we'll be assembling the system and going through testing. Below are a list of resources that I use to draw inspiration from, or projects that I've sourced designs for various components. Please take a moment to explore these resources for additional insights and show support for other makers. As always, if you have any questions about Exploration Commons or the programming we produce, please don't hesitate to reach out. Thank you for watching, and I hope you will join us next time. Take care.